Hello and welcome to this new lecture on rule-based stochastic processes. I will have to tell you that this is actually the core of the whole lecture, because I think rule-based stochastic processes are the most fertile way to describe dynamic changes in a complex system. So of course, this is at the moment a claim. We will have to go through a lot of structure, but let me just repeat that there are certain problems, for example, with differential equations. So differential equations is something you would naturally use as a mathematician to describe dynamic changes. The reason for that is that we all are very well educated in differential equations. Everybody has a course on it, etc. But the problem is that sometimes the assumptions that are implicitly used in applications of differential equations are actually not satisfied. So the most important such fact is that very often in complex systems you have a situation where certain system components or basic objects, as we call them, are not around in sufficient numbers to satisfy the kind of rate approach which you have in differential equations. So some of the events that are taking place are depending on the availability of sufficiently many basic objects in the system. For example, think about an economic situation where you need a lot of transactions, for example, in order to satisfy either a stochastic differential or just a differential equation. And sometimes there are just a few key players that buy and sell things in a market, and if they don't act at a certain moment in time, then there are just no trading events, and this will create huge fluctuations, for example, in the prices of goods, and therefore this will never be able to be described by a differential equation. So with this motivation, I really would like to emphasize again that rule-based systems are able, in their different, different interpretations, that they describe all of these things if we use them. So again, this is a very important lecture. It's, I think, really at the core of mathematical modeling in the sense to in the way to describe dynamic changes. So we have to go back to the types. We have done classifications in the lecture several times. So you have a situation where you have these basic objects in the system, and then the types are groups of basic objects that satisfy a certain property. That is exactly what classification does. So we can right away go to the next slide and introduce a little notation. So in the rule-based systems, you will always have that we assume that we have as many different such types in the system which we observe, and then we can say that the set of all types, which will be denoted by curly capital T, is just this set from T1 up to Ts. Let me emphasize that the types at the moment here are assumed not to have any internal state space. So you can imagine that many scientific problems are such that the basic objects will have a kind of internal state space. That is a problem of system closure or system, where is the system boundary. So for example, if you have a sociological or an epidemiological situation where the human individuals are, let's say, at the basis of the system, so they are the basic objects, then of course you cannot avoid saying that they have an internal state space. So if, for example, in opinion formation, they will have to form their opinion before they do something like voting or whatever, and therefore you have to attach internal state spaces to the basic objects. But this will be done in the lecture later. Here at the moment we assume that there are no internal state spaces. Yeah, you have seen this picture here several times, so I don't need to explain it again. So we have a partition of the basic object set into these types, and they form a complete covering with subsets. So every type can be interpreted as a subset of the basic object set O. And if you think back to the hypergraph introduction to the lecture, then of course you can immediately see that this is a hypergraph structure. So you can define a hypergraph which has the basic object set as the basic set, and then the types form the hyperlink, the family of subsets of O, and they are interpreted as hyperlinks. Yeah, now that is, as I said, we are at the core of the lecture with respect to dynamic changes at the moment. And now we are at the core of the formalism by introducing an event structure. So here we assume normally that we have a discrete event structure like in the Poisson process before. And the event itself will be described here always as an arrow. So you have a transition by a discrete event. It's best to start where this is coming from, and that is chemistry. So if you would have a chemical reaction, I write down a very, very simple one. So you would have something like, you have a proton, and you have, let's say, two of them, and let's say you have one oxygen atom. Then you will be able somehow, even that is not the true reaction that takes place in the real world, but formally it is a correct chemical transformation. So you will produce one molecule of water. And yeah, so this is really in this case this reaction arrow here is indeed an event. So these molecules here have to bump into each other in order to form this water molecule. And we just generalize this kind of thinking from chemistry to arbitrary rules which then apply to any system we can think of. And yeah, so you see, the most important thing in order to write down such an event structure, such an arrow, is that you have the typification in hand. Chemistry relied on this typification, of the different atoms into chemical species. But of course, here the types can be anything else. They could be different animal species or plant species in population dynamics. They could be different behavioral classes in a human population, or they could be just, for example, sexes like male and female. Things like that. So you can see already that with a typification you can enter any area of science. But now as in chemistry, you have to introduce a certain stoichiometry. and this is done by these stoichiometric coefficients here and here. So here, this left part of this rule will always be called the source. And the right part here of this event structure will be called the target. And the stoichiometry is like that. So you assume you have in the jth rule, so here we assume that we have, as I said here, in this upper part we have many rules in the system, many different rules, and the set of rules will always be denoted by this curly R. So here we could actually write this in front of this event. So this is the jth rule, which is described here, and so the index j here is always fixed in this stoichiometry on the left hand side of the rule arrow, and the alpha I j is then telling you how many objects of the type Ti you need to assemble something. So this is, in other words, this is just an assembly instruction. So you go through all the types, and the alpha I of the jth rule will tell you how many of these type objects you need in order that the event is going to happen. So again, here in this chemical reaction, you would have that 2 protons and 1 oxygen atom have to come together in order to do the reaction. Now, now if you have as many of these objects in the system, it could also be that you don't have as many objects in the system. In this case, this kind of rule or this kind of event described by the rule can never happen. So that is also very important to note. But if you have enough of these objects, then this event can happen. So you have the transition, which is given by this arrow, and then here on the right hand side, in the target side of this event structure, you have here again a stoichiometry which is given by beta ij, and then the beta ij's tell you how many objects of type Ti are created in the event. So here, for example, in this chemical reaction, you have here a stoichiometry of 1, which is not actually usually written out in chemical reactions. So, we can, but we should actually write it here for a moment. So, here the beta ij would be 1. Of course, you have also to note that is actually an interesting comment that H2O would be a molecule that is also one type. So actually, in this whole formula, you have 3 different types. One is the proton, one is the oxygen, and one is H2O. So these would be 3 different types. And you have a stoichiometry here of 1, so one of the beta ij's would be 1, and only the water type would be present here on the right hand side of the target in this specific chemical reaction above here. So that means that only one type will be present here on the right hand side, but in principle any given type of the S-types could be produced in a single event. So this is really the kind of structure. So in a single event, exactly this kind of transformation described by the stoichiometries and by the types is happening. So let's Yeah, so here that is exactly the interpretation. I think we have covered that, and I've covered this as well. So now the question is, what are these transformations saying? So here in a chemical reaction, if we go back to that slide, in a chemical reaction, you always have the assumption that you can count the atoms that are in the reaction volume. So you know how many hydrogens are there. Oh, sorry. You know how many hydrogens are there. You know how many oxygens are there, and so on. And but of course you can imagine this is not the only way. You can also, in many other areas of science, you might not only have things you can count, like atoms or people. You can, of course, also count people. But let's say, we want to have a type like we have a fluid, and that, let's say, we have water and alcohol or something like that, right? So these would be two different types. But it's usually, not a good idea just to count water. It's also not a good idea to count alcohol. So you would actually associate them with substances. We will allow for that case as well. So all of that, of course, will be imprinted in the stoichiometry. So as long as you have here the alpha chase to be integer valued, you will have a so-called system or rules of counting. And chemical reactions are interpreted as rules of counting. So you count objects. But you also have rules of amount, that's how I call them. And these will be dealing with substances. And in this case, of course, the alpha I chase cannot be only integers. They are allowed in this case of substances also to be real valued. Yeah, so they are positive real numbers. Potentially, of course, they can also be zero. That holds also in the integer case. So, for example, if a certain type in this rule is not present here, then you just set the corresponding stoichiometry here to 0. And if something is not produced in a certain reaction, because that is just the general form, then you also set one of the beta I chase to 0. And that is the same as saying this kind of type is not produced during the event. Okay, so we have here the substances. As I said, in this case, the alpha I chase will be real valued, and you have this specific interpretation of that. Now we have to go to something that will be defined on the left-hand side and on the right-hand side of the rule arrow. And these are the complexes. We have already introduced them, but here now we introduce a slightly different notation, which is sometimes useful. So remember, we had the source and the target side of a rule arrow, to the left and to the right of a rule arrow. And now, of course, you can have the idea, which is a good idea, that you think about the net production of certain types during the event. Of course, in principle, a type can occur both on the left side, on the source side of the rule arrow, and on the right hand side of the rule arrow. So you can actually define the difference Nij, which then will just be the difference of the stoichiometric coefficients. And if this is a positive number, then there will be a net production of the type in this event when the rule is applied. And we can associate, to each of the reaction or rule arrows, we can define one such so-called complex. So S is for source, J is the association for the jth rule, and so you write down now the stoichiometric coefficients not in this sum notation as we had earlier. By the way, this is called a so-called formal sum, because in the sum you have the stoichiometric coefficients and the types, so that can only be formal. It's nothing you can really sum up. But in this notation we use here a column vector, where for a certain rule you write down all the stoichiometric coefficients of the source side in this column vector. You also do this, of course, for the target side. So this will be this notation. All the betas from the right hand side, from the target side, are also written here as a column vector. And then you collect all these complexes from all the rules or reactions into a complex set. And you can, of course, then clearly see that this complex set will have 2R many entries, because you have R many arrows, rules in the system, and then you have always a source in the target side, so you have exactly 2R chemical complexes. They don't need to be different from each other, so many of these entries, of course, can be exactly the same. That can happen. And now, following this idea of net production in the event structure, we can introduce the stoichiometric matrix. So we assemble this. First, we assemble the certain submatrices, which are these net yield vectors, which we call Nj, and they will be exactly the net reproduction numbers from these different rules. So here that is the jth one, and then we collect all of these net yield vectors together in one matrix, and that then will become the stoichiometric matrix. We denote it by N, and of course the stoichiometric matrix is depending on the alpha, so the stoichiometry of the source sides, and the betas, the stoichiometry of the target sides of all rules. And then you just expand that as taking the column vectors of taking the net yield vectors as column vectors, and this exactly gives you then the entries to the stoichiometric matrix. Excuse me. Right, okay, I think I have said that. Now we are in state to introduce state spaces. So, in a sense, you have to think for a moment that our stochastic process or the dynamical systems we discuss later, of course, they are acting on a state space of the system, and we have to be very clear what the state space is. And of course, if we have these rules of counting, then where you just count objects, then because we have as many different types, you can collect the state space as something that collects the number of objects of each types. So this is also very often called the configuration of the system. And you see this is just the vector of all the numbers of objects of each type. So that is denoted by n1 up to ns. So if you think about that in terms of the basic object set, so here you have discrete objects because you can count them. So you have a covering on top of the basic object ZO. Here in this case you have just 4 different types, for example, and then each single particle or whatever it is, the basic objects, they will be here counted as how many there are of a certain type. For substances, that is of course different. Here you assume the state space is something that is a real number. So you say, for example, how many liters of water do I have at a certain moment? And this will be collected into this state space, which we call capital Xi. So here you cannot count objects, but you can measure the objects. So you know, for example, how many liters of water are so water would be type T1, and you know how many liters are there in this area, and then this would be the alcohol of our example before, and you know how many liters of alcohols there are in this of type T2, the alcohol, and so on. So you have 2 different state spaces depending on whether you can count objects or whether you want to regard them as substances or fields. Something like energy, for example, would also be something you cannot count. Yeah, now we come to the definition of rule-based systems. So this is very small. Let me just make this a little bit bigger. So essentially now we define a rule-based system as a tuple of 5 things. So this you can see here. So what did we have to do in order to describe the system so far? We had to introduce the types. So that was the classification. We had to introduce then the rules. But in order to write down the rules, you have also to define the complexes. So these are the stoichiometries on the left-hand side of any rule and on the right-hand side of any rule. Then we were introducing a state space. We call it here just S. And remember, either S can be a vector of length S of integers, telling you how many objects of a certain type are there, or in the other case where you deal with substances, you would have that S is a vector of non-negative real numbers. And then there will be something in addition which we need, and that will be the update rules, which I denote by curly U. And I have already touched this a little bit. So the update rules will tell you, when an event is happening in the system. And that is, of course, an important modeling ingredient. So, for example, in a chemical reaction, you will have to introduce U as collision updates. So you have to give the probabilities that at a certain moment in time a chemical reaction of a certain type will happen. If you do population dynamics, you will have to need to describe how likely it is that certain animals bump into each other, or that one animal meets another plant to eat it, or something like that. So all of these will be encountered in the update structure, which we'll discuss in a moment. But very important also is to see that you have to require certain axioms for the complexes. So you can write any kind of rule as as something that goes from one complex to the next. And then what we do not allow in a rule-based system is that we have rules that do nothing. So if a complex, which we call here P, would be transformed during an event exactly into itself, so that would be P to P, then this rule actually would do nothing. And we just can kick it out. So we really make the assumptions that there are no such rules which do nothing. That is our axiom 1 in the definition of rule-based systems. And then, for any complex P, there must exist another complex which we call P prime in C, such that either we have that P goes to P prime or the other way around. So axiom 2 can be phrased like that. By this kind of assumption, you make sure that every complex you have used to describe the system is somehow used in a rule. So if you have complexes that are never used in any rule, you can also just forget about them. So that's why we introduce this axiom 2. And the number 3 is exactly the same. So we also assume that the union of supports of all complexes P in the set of complexes C is then exactly given by all the types. So this is the assumption that also all the types are used in the complexes. So if certain types in the classification would never occur in any of the complexes, then you also could just kick them out. So in other words, you can say, 1 is you avoid certain transitions which do nothing. So in 2 you can say you avoid certain complexes that do nothing, and in 3 you can say you avoid types that do nothing, that occur in no complex. So this is exactly a requirement which we have for the rule-based system. So this kind of structure here with these 5 different ingredients which I discussed, plus all these axioms I introduced now, all of them together form a so-called numerical rule-based system. The word numerical refers to the fact that this is a rule-based system which somehow counts or has quantitative effects. So one event will change the number of something that is involved, or it will change the amount of substance which is involved in some of these transitions. But of course there are also non-numerical rule-based systems, and we will also discuss them at some time. Computer programs, for example, are rule-based systems which are not numerical. Let's go now to the different kinds of updates. I will just describe them briefly because we will concentrate on just 2 of them. But I think it's very good to have a list of all these updates for a moment. So what you could have now is the following. So remember, what we want to describe is what is a certain transition. So we have here a complex which we call P, and we have here, and that will be the source complex, and we have another complex here, P prime. So this arrow here is describing the event structure. But of course, events happen due to different reasons. This is now a very important discussion for modeling. So events can happen because somebody imposes the event. So for example, think about auctions. In an auction, somebody says, okay, at this moment in time, and maybe periodically, we will do something. We all come together and you can bid for something and buy it. this would be something that could be evenly spaced in time, and it can be completely deterministic. That you have the event would be completely deterministic, and therefore we call them finite difference types. The ones of you who know something about numerical analysis will immediately see that this is exactly the kind of approach in finite differences, and also difference equations, of course, use this kind of update, which is timed from outside the system, not from inside the system. But of course, finite differences have this fixed time step approach, but of course you can also have a deterministic system that uses variable time steps, but still is deterministic. So it would, for example, depend on the system state, how big the next time period is until you have to wait for the next event. So this kind of update we call a variable time step update. Now we come to the differential equation case. In some situations, so for example, if you have a classification of location, which is very, very fine graded, so you have even a continuum space, then gravitation, for example, would be something that acts continuously on the position, and therefore, if you look at this event structure, the only thing you can say is that you have a continuous update. You have no discrete events in this example of gravity pulling on some mass. You have really a continuous update of the position of the mass object, and therefore, this is not a discrete event structure. We will come to differential equations that describe such cases later. At the moment, we are more interested in the two remaining update categories. So in a chemical reaction, you really have something that is called collision update. Here we have the situation I described before. So we have a reaction volume, and with a certain probability, certain molecules come together, and they form a new molecule. And this is collision update. So you need a collision of these different atoms or molecules in order to have the event. And this, of course, you can imagine that such a collision update is very much depending on how many particles there are in the system at a certain moment in time, or how much substance there is of certain types in the system. And therefore we have to really go into detail in a later lecture on how we describe mathematically a collision update. It will turn out that a pure collision update creates no memory in the system. So you don't need to know the past in order to say what the probability is when you know the state that a certain collision happens. But this is not always the case. So again, if you, for example, use rule-based systems to describe, let's say, human populations, then humans definitely have something that is called experience, and that is something they have from the past. So they made certain transformations, and they have acquired experience, and therefore they will remember the next time the event happens, they will remember how they acted before, and therefore this memory will change the rate with which certain events happen. So it might still be a collision update, so different people, for example, bump into each other, but they all will have a different history, and therefore we have to describe this differently, and we call this a so-called generalized stochastic update. And this will be very important in many applications, so we have to discuss that in very much detail later. Now I have to introduce a very last ingredient into the system. As you know, for example, from chemical reactions, different reactions are more or less likely, or what in chemistry we would call that reactivity. And the reactivity is described by rates, which you write on top of the reaction arrow. So an example would this be this in the RJ's rule, you would have this KJ written on top of the reaction arrow. We call these weighted rules because you can imagine that the arrow is weighted by the reaction constant Kj. This is very much a weight as we discussed weights in the context of graph theory. Of course, you know, this reaction structure will also be interpreted later as a graph, as a directed graph. It's very easy to see that this will constitute a directed graph with where the vertex set V will be the complexes, so everything to the left and to the right hand side of the arrow. Yeah, you can see, and that's the most important thing to note, that this kind of reaction constant does not depend on the system state itself. Also, it will not be depending on time. So, you know, nothing, you don't heat up, for example, the reaction volume from outside. So the conditions of collisions will always stay the same. That's our assumption. And then we can have here just a constant, a reaction constant, which describes the reactivity of the rule, or it can also, so in a general non-chemistry context, it would describe, this number Kj would describe how likely it is that a certain rule will be applied. Of course, given that there is the same number of objects available in the reaction volume. But of course there is another important case, and that is there is something on top of the reaction arrow which is not a constant but a function. And now this function here can depend on time. So in this case, for example, we can describe that we heat up the reaction volume. So, you know, certain reactions become more likely because because the atoms are having more thermic energy. So they will react more easily. This you can describe by this non-autonomous incorporation of the time t. And the function also, very importantly, can be a function of the state S in the state space S. So that, for example, means that you look at the system and for example, even the basic objects might observe the system or might have the information to observe the system. Humans, for example, observe their environment all the time, and they will react differently to different situations depending on the system state. So for example, when they walk and they see a crowd, they will, for example, avoid the crowd. And that would be a state of this. If the crowd would be incorporated in the state of the system, then this would be indeed describing this kind of state dependency. Yeah, so we assume in this case that the weight is a continuous function that makes it mathematically a little bit easier to describe. But you can, in principle, of course, have any arbitrary function here. You just have then to live with the consequences of your assumptions. That's always what's happens in mathematical modeling. Yeah, now I come to the different definitions. So having now one of these 5 different update rules for the rule-based systems, we arrive now at different mathematical structures, dynamic structures. So if you have just deterministic updates, so you can think of that the updates are coming from outside the system, and trigger something inside the system, but the update structure is coming from outside. So like in a computer, so for example, a certain processor has a certain rate with which it executes something, but this rate is given as, it's a deterministic frequency with which computations are taking place. In this case, we call the rule-based system a rule-based automaton. Then we had discussed this other possibility that the updates are continuous, so we lose the discrete event structure and go to continuous updates of something. In this case, we have clearly created a dynamical system out of the rule-based system, and that is exactly in the definition here. But now we come to stochastic processes. So this is what we are really looking at the moment, because at the moment we want to have the rule-based systems as an extension of stochastic processes, especially of the counting processes. So just think about this for a moment. In the Poisson process, which is a counting process, we were just counting events. Now here in our rule-based system, we do much, much more. So we count the events. Yes, we do that, but we also say in which order the rules are applied when events are happening. So most of the time we will just have one rule being applied when a certain event happens. So we have to pick out this rule, for example. But in principle, it would also be possible that we execute all the rules, for example, in parallel. That would be a completely different process. But that's what the modeler can decide. So if you think about chemical reactions, that would be nonsense, because just one rule is applied at any one event, because it's impossible that two collisions are taking place at exactly the same time. Okay, so again, you know this notation again already. We have here a probability space. So omega here is of course now describing a reaction volume, something where the rules are applied to. And as I said, we are not only counting events, we also then look at the transformations of the system state at the same time. So, in other words, a rule-based stochastic process is a stochastic process, again, where we have introduced a random variable r, where r is, of course, a mapping from omega into the state space S. That is exactly what's written here. And it uses the rule-based system structure. So we had, again, this 5 tuple. So we have to have the classification. We have to describe what the complexes are. We have to say what our system of rules are. We have to include the state space. And we have here the system updates. But the system updates, in order to produce a stochastic process, have to be either of this collision update type or of the generalized stochastic update type. And then you have a true stochastic process, which now processes much more information when you compare it to the accounting processes. So you can already see how rich this structure is. It took quite some time to describe it. So let's go to the conclusions or to the summary. Now we introduced the rule-based or reaction-based approach to modeling. Yeah, the types now become the entities that can be transformed into each other during events. So from now on you should see how important it was to introduce our classification schemes. Because now we can say, what kind of type is transformed into which other type during events. So only now we can start to write down such rules. So we introduced these rules based on arrows. We had to define the complexes and the stoichiometric matrix. Remember, the stoichiometric matrix is taking into account the net production or net loss of something in the system. And we defined the rule-based system. Remember, it's based on the 5 tuple, and one of these update interpretations then, or two of the update interpretations then, did lead to a stochastic process, which is based on top of the rule-based system definition. Yes, so that is enough for today. Now we have to go to examples and we have to describe certain updates into more detail in order to be able to simulate the systems. That will be something we are doing now intensively. And I hope I can convince you that the rule-based systems should be at the core of dynamical modeling in science. Thank you very much.